students, welcome to Sunil's tutorial. I'm Sunil Birwani and today we'll be doing this chapter called as atoms, molecules and nuclei. Let's see the next part of this chapter, de Broglie's hypothesis. Now, Louis de Broglie, he was a French physicist. In 1924, he made a very bold suggestion that matter, which is ordinarily consists to be made up of discrete particles, that is atoms, molecules and electrons, and might exhibit even wave-like property. That means matter would exist in the form of particles as well as waves. That was his bold suggestion, right? So let's go through the history of this. De Broglie suggested that matter which ordinarily is considered to be made of discrete particles might exhibit wave-like properties. Right? Why did he say this? What was his reason for saying this? According to him, there are two fundamental forms, that is matter and energy, which manifest themselves in mutual, which manifest themselves and have to be mutually symmetrical. He said that nature loves symmetry. Right? According to him, according to this principle, two fundamental forms in which nature manifests itself should be mutually symmetrical. Two fundamental forms in which nature, two fundamental forms are matter and energy. So two fundamental forms in which nature manifests itself must be mutually symmetrical. Right? So thus he said that it is notable that since radiant energy has been shown to possess dual nature, matter should also have dual nature. Since radiant energy has been shown to possess dual nature. Dual nature, that is, it exists in the form of matter as well as waves. Hence, matter also possesses dual nature. That means that matter will also exist in the form of particles as well as waves. Next, he also said that there is close parallelism between mechanics and optics regarding their fundamental laws. There is close parallelism between mechanics and optics regarding, there is close parallelism between mechanics and optics regarding their fundamental laws. right, which govern their motion. So this thought made de Broglie put forth the relation between matter and radiation. He suggested that the probability of the behavior of matter is just like that of wave. Now matter is already in the form of particles. He also suggested that it is going to be in the form of waves. So just as a radiation is supplemented with particle characteristics, similarly a matter is supplemented with wave-like characteristics. So he said that matter therefore can exist in two forms, in the form of particles as well as in the form of waves. Matter can exist in two forms, in the form of particles as well as in the form of waves. The matter waves, every matter has some wave associated with it. This wave which is associated with the matter, he called this wave as de Broglie's wave. So he said that there's a close parallelism between mechanics and optics regarding the fundamental laws. So just as radiation is supplemented with particle characteristics, is supplemented with particle characteristics, just as radiation is supplemented with particle characteristics, so also matter can be assigned wave nature for full understanding of its behavior. So also matter can be assigned wave nature, right? He also said that these matter waves suggested by de Broglie are called as de Broglie's waves. These matter waves are also called as pilot waves. So some authors refer to them as de Broglie's waves, some authors refer to them as pilot waves. So I can say that matter waves suggested by de Broglie are called de Broglie waves or pilot waves. Now let us see the derivation of de Broglie's waves, and let us now see what is de Broglie's hypothesis. So in short, what is de Broglie's hypothesis? He said that there is dual nature of matter. Matter can exist in the form of particles as well as wave. Okay. Now, what is de Broglie's hypothesis? Right, the law says, de Broglie's hypothesis law says that every moving particle is associated with a wave. Every moving particle is associated with a wave. Every moving particle is associated with a wave which controls the particle in every respect. Which controls the particle in every respect. Which controls the particle in every respect. The wave which is associated with a particle is called as the wave which is associated with a particle. A wave which is associated with a particle is called as matter wave. As matter wave or de Broglie's wave. Right? Now let's try to derive an expression for de Broglie's waves. Expression for de Broglie's wave. Now, de Broglie proposed that the wavelength of the material particles would be related to its momentum. According to de Broglie, he said that whatever is the wave, it will have some wavelength and that will be related to its momentum. So he suggested that he proposed that the wavelength of material particles would be related to its momentum. Why? In a similar manner as for protons. In a similar manner as for a photon. That means the wavelength is going to be proportional, will have some proportionality with the momentum. So he came up with the expression that the momentum is going to be h upon wavelength. He said that there is some proportionality between the momentum and wavelength, and he said that let us assume that momentum is equal to h upon wavelength. Fine. Thus, he said that the wavelength associated with a particle is inversely proportional to momentum. Therefore, the wavelength associated with a particle is inversely proportional to wavelength associated with a particle is inversely proportional to its momentum. Fine. Therefore, he said that lambda is inversely proportional to p, right? Where p he called as momentum, and that's how he came up with the expression that p is equal to h upon lambda, where p is momentum, lambda is wavelength, and h is Planck's constant, right? Now, thus, what will be de Broglie's wavelength? I can therefore say that lambda is going to be h upon p, but p, momentum, we know is nothing but the product of mass and velocity. Therefore, I can say that this is equal to h upon mv, where v is the velocity. So that's how you can find out de Broglie's wavelength. De Broglie's wavelength is h upon mv, where m is the mass of the particle and v is the velocity of the particle. Fine. So that's how you found this out. Now, how did he derive this? This is my expression for de Broglie's waves. The expression for de Broglie's wave is lambda is equal to h upon mv. Right? Now, let's derive de Broglie's wavelength. Derive de Broglie's wavelength. How do I derive this de Broglie's wavelength? Now, according to Planck's quantum theory, of radiation, if I apply Planck's quantum theory of radiation, I can say that the energy in the photon of frequency of radiation and wavelength is given by energy of a photon of frequency of radiation let's assume that the frequency of the photon is V and wavelength lambda is given by E is equal to hv, right, where V is the frequency here. Now I can say that, now if I consider Einstein's equation, I can say by Einstein's equation, I can say that E is equal to mc square, energy is equal to mass into square of velocity, where c is velocity of light, right? Both are E, therefore I can say from equation 1 and 2, hv should be equal to mc square. Both relate to energy, therefore E should be equal to mc square. Therefore I can say that mc is hv upon c, c square can be split up as c into c. One c I am bringing up in the denominator, but mc is nothing but momentum, but I can say mc is equal to momentum, right? So I can therefore say that mc is nothing but p. I can also say that therefore P is equal to hv upon c, right? Now this can be written as hv upon c, frequency upon velocity, right? I can say what frequency, I can say that V upon C is 1 upon lambda, right? Velocity is frequency into wavelength. Nice. Velocity is frequency into wavelength, therefore I will get V upon C is 1 upon lambda. So V upon C can be substituted as lambda, therefore I will get P is equal to h upon lambda, and that's my de Broglie's expression. But we have also just said that momentum is equal to, therefore I can say lambda is equal to h upon p, lambda is equal to h upon mc. That's my derivation of de Broglie's wavelength. Fine, do we get this in here? So this is the de Broglie's wave equation for material wavelength. Now here we are assuming, it should be noted that the mass is a relative mass of the particle of the equation. Now when I consider this, I am assuming m to be the mass of the particle when the particle is at rest, but in reality the particle is not at rest, it is moving with some velocity, right? Now if you remember your rotational motion, mass of a stationary body and a mass of a body which is in circular motion is different, which was called as moment of inertia. Similarly here, since the particle is moving, mass of the particle at rest and the mass of the particle when it is moving is going to be different. So what is going to be the actual mass of the particle? I can say that when the velocity of the particle, velocity v of the particle is comparable, and the velocity v of the particle is comparable to the velocity of light, comparable to the velocity of light, then the mass is called as relativistic mass. Then the mass m is called as relativistic mass, which is given by m is equal to m0 upon square root of 1 minus v square upon c square, right? So here you have to make sure that you consider the mass of the particle. Which mass of the particle you consider? You consider the relativistic mass of the particle. What is relativistic mass of the particle? Since the particle is going to be in motion, it is going to have a mass which is going to be different than the mass of the particle at rest, and that mass of the particle when the particle is in motion is called as relativistic mass of the particle. Fine, do we get this thing clear? Now, so do we understand de Broglie's hypothesis? So in this case, let's consider that if V is 0, if the particle is at rest, if V is 0, that is particle is at rest. Now if the particle is at rest, then what will happen to lambda? Lambda will become equal to infinity. I can say then lambda would tend to infinity, right? That is, if the wavelength of the material particle at rest is infinity. So therefore the wavelength of material particle at rest is infinity. Fine, do we get this thing clear? So, do we understand this? Next, let's move on to the wavelength of electron. Now that we know that you can find out the dual nature of particle, that means electron should also have dual nature. It should be in particle form as well as wave form. Now if electron is in wave form, it should have some wavelength. Let us try to find out the wavelength of electron. Now let us consider that an electron at rest is accelerated through a potential difference of v volt. Let an electron at rest be accelerated. Let an electron at rest be accelerated through a potential difference of v, right? By potential difference of v volts and velocity v. So an electron is being accelerated by supplying it with a potential difference of v volt through a velocity of v. Let's assume m is the mass and e is the charge of the electron. M is mass of electron and E is the charge on electron, right? In that case, I can say that the work done on the electron is going to be nothing but EV. That is going to be the work done on the electron, right? That is the potential difference into the charge. Now, what will be kinetic energy gained by the electron? The kinetic energy gained by the electron. Kinetic energy is nothing but half mv square, right? So in that case, kinetic energy gained by the electron is going to be half mv square. From where did this kinetic energy come? This came because of the work that was done on the electron. Hence, I can say that the work done on the electron is stored in the form of energy, which is my kinetic energy. Therefore, I can say that EV is equal to half mv square. EV is equal to half mv square. Therefore, I could say that PV 2 EV upon m is v square. Therefore, I'll get v is square root of 2 EV upon m. So the velocity of the electron is going to be nothing but 2 EV upon m. Now let us assume that lambda is the de Broglie's wavelength associated with the electron. If lambda is the de Broglie's wavelength associated with the electron. If lambda is the de Broglie's wavelength associated with the electron, then I can say that lambda is equal to h upon mb. We've already derived this equation, right? We've also found out the value of v, therefore I can say that lambda is equal to h upon mv. V can be written as 2 ev upon m, right? We just found out the value of velocity to be 2 ev upon m. Now here lambda therefore can be written as h upon square root of 2 evm. Right? Do we get this thing here? Root of m and m will get cancelled. Here everything is constant. I can say that, but h is Planck's constant, which is 6.62 into 10 raised to minus 34 joule second. E is the charge on electron, which is 1.6 into 10 raised to minus 19 coulombs, and m is the mass of electron, which is 9 into 10 raised to minus 31 kgs. So in which case, if I substitute all this, I will get the value of wavelength to be 12.27 into 10 raised to minus 10 upon square root of v meters. That will be the wavelength, which can be written as lambda is going to be 12.27 upon square root of potential difference Armstrong units. That will be the wavelength of an electron. Right? Do we get this thing clear? So, what we understand from this formula is that it must be noted that the above formula is applicable to electron wavelength at low energy and low voltage. At high values, that means if I take few kilovolts of energy, few kilovolts of potential difference, the electron energy becomes so large that the relativistic mass has to be considered. In which case, then the momentum would be calculated by using the relativistic mass and not the actual mass of the particle. Right? If I am giving it a very small potential difference, then the particle electron is going to move with a very small velocity, therefore I can consider the mass of the particle. But if very high potential difference is given, then the particle is going to be moving at very high velocity, and in which case I will have to consider the relativistic mass of the particle. Right? Now, question: if you have dual nature of every particle, why is it that you are not able to see it? If matter can exist in two forms, in particle form as well as wave form, I should be able to convert my body into wave form, and waves I should be able to convert into particle. Question: why am I not able to do that? Right? Now let's consider, we've derived an equation for electron. Let us consider this for microscopic bodies. Why is it that macroscopic bodies do not exhibit wave nature? Macroscopic bodies do not exhibit wave nature. Why is it that microscopic bodies do not exhibit wave nature? Right? Let us consider a body of mass. Consider a body of mass 1 kg. Let us consider a body of mass 1 kg moving with a velocity of 10,000 meters per second, which seems highly improbable, but let us assume. In that case, the momentum of the body P will be equal to mv, right, which will be nothing but 1 into 10,000, so that will be nothing but 10,000 meters per second. That will be the momentum of the body. Now de Broglie's wavelength lambda is given by the formula h by p, right? H we know is 6.63 into 10 raised to minus 34 upon 10,000, right? In which case you will get the value of lambda as 6.63 into 10 raised to minus 30 meters. Now, this definitely is too small a wavelength and certainly beyond measurement, and that is the reason why macroscopic bodies do not exhibit dual nature, right? This is a very small wavelength. This is a very small wavelength and certainly beyond measurement, right? It is for this reason that microscopic bodies in the world do not exhibit wavelength. It is for this reason macroscopic bodies of the world do not exhibit wave property. Right? So we understand why macroscopic bodies do not exhibit wave properties. Now let us try to find out the relationship between de Broglie's wavelength and Bohr's atomic theory. Right? Let's consider how de Broglie's hypothesis leads to Bohr's second postulate. Derive Bohr's second postulate using de Broglie's hypothesis. Let us see how do I get Bohr's second postulate by using de Broglie's hypothesis. Right? Now let the electron in hydrogen atom of Bohr's second postulate be replaced by a matter wave of wavelength lambda. For Bohr's postulate we consider hydrogen atom. That hydrogen atom will have an electron. Electron can exhibit both in particle as well as wave form. Let us assume that electron is in wave form. If it is in wave form, it will have some wavelength. Let us assume lambda is the wavelength of that electron. So we say that let the electron in hydrogen atom in Bohr's second postulate be replaced by matter wave of wavelength lambda. Let's assume that lambda is the wavelength of the matter wave that is replacing the electron. Now, for stability in electronic orbit, it is essential that there must this particular wave should be an integral number of the wave in the orbit. I can say that for stability of electronic orbit, it is essential that there must be integral number of waves in the orbit. Integral number of waves in the orbit. I cannot have decimal number of waves, right? If not, so the waves would go on interfering with each other. Suppose if they are not an integral number, then If not so, the waves would go on interfering with each other. The waves would go on interfering each other. That means I can therefore say that 2 pi r n circumference should be equal to n times lambda, where n has to be an integral number, where n is equal to 1, 2, 3 and so on, right? Therefore I can say that lambda, why did I consider 2 pi r? Because that is the circumference that the electron has to cover, so that is the distance that the wave would have to cover, right? It should be, and distance is nothing but lambda. The distance of the wave is nothing but lambda, so 2 pi r should be lambda, and it has to be an integral multiple, therefore I am multiplying it by n, right? It could be some multiple of lambda, so therefore I can say lambda is nothing but 2 pi rn upon n, right? Now if I apply de Broglie's wavelength by de Broglie's wavelength, de Broglie's wavelength says that lambda is h upon p. That means I can therefore say that h upon p is nothing but 2 pi rn by n, right? Therefore I can say that nh upon 2 pi is nothing but p into rn, right? Now p into rn, momentum into radius. Momentum into radius is nothing but angular momentum. Now according to Bohr's second postulate, if I apply Bohr's second postulate, angular momentum of the electron, angular momentum of electron is given by L is equal to nh upon 2 pi. De Broglie's hypothesis also says that, right? By de Broglie's hypothesis, or I could say that angular momentum is equal to mv into rn, linear momentum into radius, which is nothing but pv, p into rn, linear momentum into rn. Now by de Broglie's hypothesis I found out that angular momentum is nh upon 2 pi, and Bohr's second postulate also says that angular momentum is nh upon 2 pi. Therefore it is clear that de Broglie's hypothesis leads to Bohr's second postulate. From de Broglie's hypothesis, if I apply de Broglie's hypothesis, I get L is equal to nh by 2 pi, and by Bohr's second postulate also L is equal to nh by 2 pi. Therefore I can say that de Broglie's hypothesis leads to Bohr's second postulate. Therefore de Broglie's hypothesis leads to Bohr's second postulate. Right, that's how you get this. Right, we stop this here for the day. Thank you very much.